In my previous video, I showed you a nice design for a toroidal propeller. It's not bad, but of course it's not perfect. One of the more glaring issues is the blade pitch. Because it sweeps from a root profile towards the midpoint rotated 90 degrees, the pitch of the blade increases outward from the hub. This is almost certainly exactly the opposite of what we want. Since as we move outward, the linear speed of the blade increases, we might prefer the pitch to get more shallow. Can't carry this to the final extreme because a fundamental of the design is that we must turn up towards a 90-degree angle at the tip in order to loop around. However, we don't have to do that turn uniformly throughout the length of the blade. Fortunately, parametric CAD is very much an iterative process. We can add additional profiles along the length of the blade to more tightly control the pitch. So let's begin. We can more tightly control the blade pitch along its length by passing the sweep through additional profiles. The additional profiles will be clones of the blade profile mapped into place. We will need appropriate reference points for the mapping. The first reference point, of course, will be the blend curve. We'll need a second to place it appropriately along the span of the blade, so we'll add it to the midpoint scaffold. Open the midpoint scaffold sketch, add a point of real geometry, and constrain it to be along the scaffold line. Now constrain its distance from the center of the hub, let's say 40 millimeters. Name the constraint pre-mid-span. While the midpoint scaffold is selected, go to the Appearance tab and increase the point size to 8. This doesn't make any changes to the actual geometry, but it does make the point larger on the GUI so we can more easily select it later. Now I'll hide away most of the geometry of the blade so I can see to do the mapping. Clone the blade profile, name it Lower Pre-Mid Profile. Now we'll go into the mapping. First select the blend curve. It defaults to the Frenet or Frenet in B, meaning normal to the curve. This is what we want. For the second reference point, I'll select the new real geometry point that we added to the midpoint scaffold. Effectively, this slides the profile along the blend curve until it reaches a point where the second reference is coplanar to the sketch. This can all be solved mathematically and has one solution in real space. But we're going to let FreeCAD take care of that for us. Now repeat the process for the upper blade. Now that we can see how it lays out, it appears that 40 millimeters was a little too much. So we select the mid-scaffold and come down into the data pane under Constraints and change the pre-mid span to 35. That looks a lot better. Finally, we adjust the pitch of the pre-mid profiles by selecting them and changing the attachment angle in the data pane. We're ready to add the profiles to the blade sweeps. Select the lower blade sweep and go to the data pane and click Sections. Now click the button to the right to bring up the dialog box. The dialog is a little bit quirky in that it shows us the sections that are part of the sweep, but it doesn't say anything about the order. Instead, the order of sections in the list will be determined by the order they're selected in the dialog. So first we have to click Clear to start over. Now we select the sections in the order they will appear in the sweep. Start with the lower blade profile, then the lower pre-mid profile, and finally the mid-blade profile. Click OK. Now repeat this process for the upper blade. Now let's unhide the blade geometry and see how we did. The draft plane is getting in the way, so I'll quickly go into the draft workbench and hide it. As you can see now, rather than the blade curving gently through the entire span from the pitch at the root to 90 degrees at the midpoint, the pitch remains more or less constant through the majority of the blade and then twists more acutely towards the end. This is what we were wanting. Keep in mind it can only twist so sharply before the geometry breaks. It's just as well, since in the real world if it twisted too quickly it would tend to look like a brick wall to the airstream and cause turbulence. That's all looking good. So bring back the rest of the propeller. Now that we have better control, we can make some adjustments to the pitch. Keep in mind when adjusting the pre-mid pitch that because of the way we've set up the attachment, it may need to be a degree or two greater than the root pitch in order to keep the blade at a constant angle if it is desired. Adjusting name constraints and attachment angles in the data pane is a useful technique for modifying our design, but to really bring it together, it's best to move everything into a spreadsheet. The actual process of doing that is outside of the scope of this video, but if you're interested in seeing it, I'll be posting a companion video showing the technique. For now, we'll just assume it was done by magic spreadsheet elves. Now that we have a nice spreadsheet, I have arranged the display so we don't have to keep flipping back and forth between tabs. I went to Windows, Tile, and then adjusted the size of the spreadsheet window and the model window so that we can both work on the spreadsheet and see the results at the same time. One of the most common designs is a two-bladed drone propeller, so let's make a few changes to come up with one of those. We set the number of blades to 2 and we'll set the blade angle to 180. Immediately something goes wrong. This can be a little hard to diagnose, but what it comes down to is that we have pushed the geometry of the blade a little too far. The blade is only 0.6 millimeters thick, so as it has been manipulated, somewhere an edge was rounded down to an anomalous 0 thickness solid. By increasing the thickness to 0.8 millimeters, we resolved the issue and the blade geometry is computed properly. The next difficulty we notice is that now the blades are sticking out of the top of the hub. We could reduce the offset of the blades, but that would change aerodynamic properties. Instead, we can just increase the height of the hub a little bit so that it properly encloses the roots of the blades. With the spreadsheet, we can easily adjust the blades to whatever span we might need. For example, let's try 150 millimeters. Since that's the span of a single blade, it'll result in a fairly large propeller. Obviously, this will require an adjustment to the mid-span as well. Let's go with 120 millimeters. With that done, the profile of the blade is looking a little bit anemic, so increase the chord to 14 millimeters. Now the hub looks comically tiny and doesn't even begin to accommodate the actual root of the blades. So increase the diameter of the hub, let's say to 20 millimeters. Because the chord of the blades is increased, the hub no longer encloses them, so increase the height of it to 8 millimeters. I think I'd like a little bit more pitch to the blade. Increase the lower pitch to 35 degrees and increase the lower mid pitch to 37 degrees. Similarly, modify the upper blade. Again, now that we've increased the pitch, the hub is no longer tall enough, so increase it to 12 millimeters. Now just for fun, we'll try a 3-bladed propeller. First, set the blade angle back to 120 degrees and set the count to 3. As you can see, we now have segments of the blade intersecting each other. For 3D printing, that might not be the worst thing in the world, but it is probably not quite ideal either. If we were machining this, it could be a real nightmare. A simple solution to that is to increase the offset between the lower and upper blade. Giving that some thought, it sounds like something that should really be in the spreadsheet. So I'll add a line for the root Z offset and set the current value to 1 millimeter, matching what we have now. Set the alias to root Z off. Set the position of the root anchors to use the spreadsheet value. To keep things symmetrical, I'll just use a single value for the offset, and we'll set the lower blade position to negative spreadsheet.rootZ off. I'll set the upper blade position to spreadsheet.rootZ off. Now that it's in the spreadsheet, increase the offset to 3. That eliminates the overlap between the blades. But now one more time we need to increase the hub height, this time to 16 millimeters. So now with better control over the blade pitch and the spreadsheet to bring it all together, we can easily produce a wide variety of variations on the theme of the toroidal propeller. Now it's just a matter of determining what works best and fitting it into our application. Thank you for watching. If you liked this video or found it useful, please like, subscribe, and share. If there's anything you'd like to see covered here, please let me know in the comments below.